Welcome back. So today we're going to start a completely new topic, which is fluids. Fluids means anything that flows. So as you might imagine, water is an example of a fluid because it flows, but so is air, so is honey. So all gases and all liquids are fluids. So this includes liquids and gases. And the study of fluids helps us in a lot of things. For example, if you've ever wondered how an airplane can fly, it's because of the study of how fluids move, which is called fluid dynamics. So the first thing we need to consider when talking about fluids is that the mass of a fluid doesn't give us as much information as when we're talking about a solid. What we care the most about in terms of fluids is its density. Density is equal to mass over volume. So basically what we're talking about with density is figuring out how packed the molecules in a substance are. The greater the density, the more packed they are, the more mass there is in a smaller volume. So the letter that we use to represent density is called rho. So this is mass over volume. And the units for mass are kilograms, and the units for volume are cubic meters. So the unit for density will be kilograms per cubic meters. Now we're going to learn about two specific things about fluids today. We're going to learn about something called hydrostatic pressure, or the pressure that fluids make, and we're going to learn about the force that fluids make to make objects float or some objects sink, and that is called the buoyant force. Buoyant force or fuerza empuje. So let's start with pressure. So pressure has its own equation, which is force over area. So basically an object feels a greater pressure if there's more force acting on it, or if the area that the force acts on is smaller. So it's proportional to force, inversely proportional to area. So the equation is P, capital letter P, equals force over area, F over A. So that's why it's important to write density as a different kind of P, because if not, you're going to get confused between density and pressure. This is not a P, this is a P. Okay, and the unit is the unit of force, which is newtons, over the unit of area, which is cubic meters. So this unit, because it's so common, it's given its own name, which is Pascal, and written PA. So this is a unit of pressure called Pascal. So because every object, every fluid causes a pressure, we actually feel a pressure due to all the air that is on top of us. It has a weight, even though it doesn't seem like much, and it's making some pressure over us. So that is actually called atmospheric pressure. It's the pressure that the air makes over us when we're at sea level. So the atmospheric pressure at sea level actually has a value of 101,325 pascals. There's actually many units of pressure, but another very commonly used unit of pressure is called the atmosphere. And this is actually equal to 1 atmosphere, which just makes sense. So if you want to convert between atmospheres and pascals, you need to divide pascals by 101,325. So for example, you know that when you go into a pool and you go to the bottom, you feel a lot of pressure. Sometimes your ears start hurting and it's harder to breathe. You feel like your lungs are also getting crushed in. So that's because not only do you have the pressure of the whole atmosphere on top of you, but you also have a pressure from the water that's over you. Since the water is so much more dense, it has so much more mass per volume than air, then even 2, 3, 4 meters of water make a lot of pressure compared to the atmospheric pressure. So the equation, if you wanted to figure out the total amount of pressure acting on you, which we would call the total pressure, P tot, you would have to add the atmospheric pressure plus the pressure done to you by the fluid or by the pool in this example. So this is what we call the hydrostatic pressure. So this is hydrostatic or fluid pressure. And this one actually has an equation that you can use to figure it out. So this P of the fluid, let's call it PF, P hydrostatic, it's the same thing. The equation is rho times G times H. So rho is the density, right? Density. G is the constant, the acceleration due to gravity, 9.8, positive 9.8 meters per second squared. And H is actually the height of water that is above you. So how far beneath the surface you are. So height of fluid. It's always positive. So let's do an example up here. Imagine you're underneath the pool, at the bottom of the pool that is almost 3 meters deep. So 2.75 meters deep. What pressure will you feel in total? So what we need to do first is calculate this P with this equation. So the hydrostatic or fluid pressure will be equal to density times 9.8 times the height. So the density, actually the density of pools or of pure water, clean water, H2O, is 1,000 kilograms per cubic meter. So we can remember that. This is always the case, 1,000 kilograms per cubic meter. So we put that into the equation, 1,000, we multiply by 9.8, and we multiply by the depth of the pool that you're under. So 2.75 meters of water. And this actually gives us 27,000 pascals. So if we want to find the total pressure that we're under, we have to add that to the atmospheric pressure, which is 101,000. So 101,325 plus 27,000, we're going to be under 128,325 pascals of pressure. So it's quite a bit. It's like 1/4 extra of the atmospheric pressure on top of you just for being a couple of meters underneath the pool. Now let's talk about buoyant force, fuerza empuje. 3 centuries before Christ, in the Greek Empire, there was this guy called Archimedes. Maybe you've heard his name. And he was known for being a very smart scientist. So one day, the king, he had his crown and he was wondering if his crown was really pure gold or if it wasn't pure gold. And he thought to ask the scientist of the empire. So Archimedes was thinking how he could figure out if the crown was made out of pure gold. So what he thought was the density of gold was a known value. Everyone knew, scientists knew, it was tabulated, the density of gold. So if he could just figure out the density of the crown, and it gave him exactly the same as the density of gold, then he could prove that the crown was actually 100% gold. So density, as we said before, density is mass over volume. And he knew the mass of the crown. He could weigh it, he had a scale, but he didn't know how to figure out the volume of the crown. Because how do you figure out the volume of something that is not a cube or a circle or something that you can actually calculate the formula for? So he was showering, he was in his tub when he had a very smart idea. And actually, legend has it that when he had this idea, he ran out of the tub and went naked throughout the whole town and shouted, "Eureka!" So what he figured out is that if he has a tub with water, filled to the brim with water, and he puts something inside it that sinks, so let's say he has the crown, when it's down here, since the crown is occupying that space, the water can't be occupying that space anymore. So where did the water go? The water was actually forced to flow outside and fall out. So if you can pick the water that fell and measure it, for example, if you have a graduated cylinder here, and you can measure the amount of water that came out of the tub, you know exactly the volume of the crown. But when do objects sink? So we know already, we figured out that when an object has a density bigger than the density of the fluid, it sinks. And when its density is less than the density of the fluid, it floats in that fluid. So let's write that down. The density of the object, let's call it is bigger than the density of the fluid, then it's going to sink. If the density of the object is less than the density of the fluid, it's going to float. But why? If it's always the same object, why does it sometimes float and why does it sometimes sink? So here's the thing. You have an object, let's say again our crown, it's in water. And let's suppose it sinks but not to the bottom. It just sinks enough to be here. Let's just draw it as a little ball. So we know about forces, we know about free body diagrams. We know there's a force acting on this object and it's its weight downwards. So here we have the force of gravity downwards. But if the object is in equilibrium there, it's staying still there, it has to have a force pushing it upwards that is the same size of the weight. So there has to be another force here. What force is that? It's the force that fluids make on the object that makes it go up. That force is called buoyant force, or fuerza empuje. Buoyant force is this upward force. So buoyant force is always upwards, and it has to do with the fact that pressure at the bottom is bigger than pressure at the top from what we saw before. So there's a difference in pressure that makes the water want to push the object upwards always. So the weight is always the same for all balls. But if you have it in a substance where the density of that substance is less, then that means that this buoyant force will be less and the force of gravity will be bigger and it'll sink. If instead the fluid is more dense, a lot more dense, it will make more of a force upwards and it will be bigger than the weight and the object will float. So what's the equation for buoyant force? So we're going to write it as FB, and the equation is actually density of the fluid times G times the volume of fluid displaced by the object. Displaced by the object. So in this example, it would be the volume of the crown. In this example, it would be the volume of the ball. And again, the G is 9.8, the acceleration due to gravity. But careful here. What if the ball is only half submerged? So let's say we have a ball that is lighter, it's maybe made of wood, and the water is until here. So because it floats, only half of the ball is submerged. Only half of the ball is submerged underneath the water. So the volume of water displaced is only half of the ball's volume. And if, for example, the ball floats a lot more, and let's say the water is until here, and the ball is basically just completely floating, like let's say a piece of wood, then there's no displaced water, or almost no displaced water. So the volume that you put here is not the volume of the object, it's the volume of displaced fluid. Right? So how much water would have fallen out if you had put the object on top? And the more it floats, the less water is displaced. But then there's something called Archimedes' principle. So when Archimedes had this experience and said eureka and had his great idea, he discovered something. And it's that this thing, this equation over here, is equal to the weight of fluid displaced. So what he did basically, and what we now call Archimedes' principle, is that the buoyant force is equal to the weight of fluid displaced. So in the example of the crown, if you measure the weight, if you put this on a scale and you measure the weight of the fluid displaced, you know exactly the buoyant force that was acting on it. Okay, so we have two equations for buoyant force that we can use. We can use this long one if we're given the volume of fluid, if we're given the density of the fluid, or we can use this small one if we know the weight of fluid displaced, mass times 9.8. So another example just to make it a little bit more clear. So suppose we have, again, two glasses with water, exactly the same, and we put in the middle two balls. But one is really light, like it's made out of wood, And the other one, we put a ball that is made out of metal. So it's very heavy, very dense. So if we let go of the two balls, what will happen? So the first thing we need to do is measure the buoyant force. The two balls are in the same fluid, both in water. So the density of fluid is going to be the same. 9.8 is a constant, and the volume of fluid displaced, if the volume of the balls are the same, then the volume of fluid displaced will be exactly the same. So notice that both balls will feel the same amount of buoyant force, exactly the same amount. So here we can draw arrows of the same size. But what's the difference? The weight of this ball is bigger than the buoyant force because it's very heavy and very dense, while the weight of this ball is almost nothing because it's really light and it doesn't have much density. So the result will be that this ball will go upwards because it has a resultant force upwards, and this ball will go downwards because it has a resultant force downwards. So even though the buoyant force was the same, this ball will float and this ball will sink. 3 misconceptions, 3 things that people usually get wrong that you have to keep in mind. One thing, the only thing that we care about the object is the amount of fluid that it displaced. We don't care about the density of the object for the equation. We only put in the equation fluid values. So this is the density of the fluid, not of the object. And this is not the volume of the object. It's the volume of displaced fluid or the volume of object that is submerged. So that's the second thing. Don't take into account the whole volume. Figure out what percentage of the volume is underneath the fluid to calculate that volume. And the third thing is that it doesn't matter the height at which it is. Because look, the equation doesn't have h. The h was only on the pressure equation, but not on the force equation. So we could have put the balls here or underneath 2 kilometers of ocean, and the result would have been the same. Let's do an example and we'll be done with this topic. So suppose we have a woman and she's scuba diving at a depth of 35 meters. Her mass is 65 kilograms and her volume is 0.65 times 10 to the negative 3 cubic meters. If she's scuba diving in pure H2O, pure water, what will be the buoyant force that she feels? So what is her buoyant force? So the buoyant force, we need to go back to our equation, is the density of fluid times 9.8 times the volume of fluid that she displaces. So in this case, the density of the fluid, since it's pure water, is again 1,000 kilograms per cubic meter. G, 9.8 meters per second squared. And the volume of water displaced, since she's scuba diving, she's completely underneath the water. So we're going to take her entire volume. If she was floating, we wouldn't take her entire volume, only the volume that was underneath the water. So the volume is 0.65 times 10 to the negative 3 cubic meters. So this cancels with this cancels with this, and we have newtons, kilograms meters per second squared, which is newtons. So this will actually give us 6.4 newtons. That is the force that she feels. So important things to notice about this example, we didn't care about her mass. The mass is not important, only things about the fluid. And we didn't care about the depth at which she was. We don't care about the depth of fluid, only, again, the density of the fluid and the volume of fluid displaced.